So today I'm going to show you how to create a molecular input file for CrystalGrower using the software Topos. So the first thing you need to do is have Topos installed on your computer. Once you have it installed, go to this System Topos Parameters options, move to Output, and make sure that the Crystal Growth option is selected. This means it'll write out the correct format for CrystalGrower. You can also decide whether you want to output multiple files at once or single files. Generally for molecular you would stick to single files as you'd be studying them as you make them. Once you've selected that, press OK. Now we need to create a database to read our molecular CIF files from, because this is the file we will start from. So if I go to Database, New, it first opens a standard directory. So if I navigate to somewhere a bit more useful to me, I'll go to my work folder and into my Topos folder that I've created, and let's go into this tutorial video folder, and we'll call this database tutorial. The .cmp is the format for a Topos database. So I press open, asks do you want to create the database, press yes, and it asks for your user code. The number you put in here is just the number 1, and you press enter or click OK. So you see this has now created a database in Topos. So we want to populate this with CIF files that we want to study. So the first thing you have to do is close it, because Topos needs it to be closed to access it the first time. You then click database, import, and you'll see it's filtering looking for CIF files. So this is how you import them to Topos. So I'll go to my CIF files folder, and I've got a set of a few different kinds of CIF files in here that I want to study. You can select all of these at once or one at a time, whichever ones you want, and press open. And then it will open another window, but you can see this time it's searching for CMP, which was the file format for the Topos database. So we'll go back to our tutorial video folder and open our Topos database that we wanted. So you can see now that it's imported all these different CIF files that I had before. But you can see it's given them the names based off of what appears in the CIF file. So a lot of the times you want to change these to match something that makes more sense to you. So now that we've renamed our CIF files to explain what structures they represent, we can go through the process of calculating the bonding information for them. So when you read in a CIF file to Topos, the bonding information is not stored, so we need to recalculate it for the intramolecular bonds, but we also need to identify the interactions to the neighbors, so intermolecular bonds like hydrogen bonds and van der Waals interactions. CrystalGrower needs these to figure out the neighboring molecules in the crystal. So if I double click this database entry for urea, this is the one we'll look at first, you can see it's read in a lot of the information from the CIF file, so the year of publication. It's also then got all the information about the unit cell, and it has like the space group and stuff like that. If you go to the Atoms tab, you can see it has all the information about the symmetry of the molecules and the atoms in the CIF file. And you'll see this column here, this coordination number is 0 because it hasn't read any bonding information in. So we need to regenerate this bonding information. And when we do that, it will create a new tab in here, which is the adjacency matrix, which gives you all the descriptions of the connectivity in the CIF file. So to do that, we need to use this AutoCN, which is the module in Topos for calculating molecular interactions and atomic interactions. So if I click this symbol here or press Ctrl N on the keyboard, it'll open up this window here. You click Options, and you leave pretty much everything else the same. You just go to this matrix window here. And it might seem complicated at first, there's a lot of choices, but a few of these simple ones can just work straight away. It's only if it doesn't give you the result you want that you have to go in and start delving into the more advanced options. All of these options are described in a written guide as well, if that's better than this video. So we'll start just by clicking domains as the method for calculating all the interactions. The domains will be connected to this minimum omega value here. So this is kind of an interaction strength descriptor right here. So a lower number will identify more weaker interactions as well as the stronger ones, and a higher number will only identify the strongest of interactions. These are kind of tied to Voronoi polyhedra and their face sizes. That's how these are calculated. So if I just set that as 1, quite a low number, and press run here. So it comes up with this result window which tells you the types of interactions and the coordination number of each of these atoms in the unit cell. So it's given quite a lot of van der Waals interactions and quite a few hydrogen bonding interactions here. So we can visualize these interactions that we've created by using another module within Topos, which is IsoCryst. So that this little pencil symbol here, or Control I on your keyboard, brings up like a visualization window. But you can see it hasn't shown you any molecules yet, so the first thing you have to do is press the pencil here, or the plant symbol to grow your crystal. So press the pencil, and you can see it's drawn a urea molecule. You can click a lot of these options here to give you different visualization options, but I'll just quickly go through it. So you can see there that we've got our urea molecules, well, fragments, because they're stretching across the unit cell boundary. And you can see we've got the valence bonds between the atoms. So if I click valence here, I can turn them on and off. And then we've also got hydrogen bonds. They're dotted between atoms. So I click that, turn those on and off. And then we've got van der Waals interactions. These are also dashed bonds, so I can turn these on and off as well. So that's given us our bonding information. We can verify this bonding information by double-clicking the database entry again and seeing that this new adjacency matrix tab has been created. So as well as visualizing the atoms, we can actually quantify them as well, the interactions. So we can expand and contract these windows, and you can even right-click and expand all of them. And there's a lot of other options you can do to select certain interactions. You can mark equivalent interactions by point group, mark equivalent interactions by space group as well. There's lots of things you could do. So the main thing that you can spot here as well is the different coloring of bonds. So if they're bold, they are valence bonds. If they are not bold, they are van der Waals interactions. And if they are bold and blue, they are hydrogen bonding interactions. You can also have red and bold, that's a specific bond. And you can have not bold but crossed out. That's a missing bond or no bond removed or something like that. So now that we're happy with our connections, we can actually generate the structure file. So what we need to do is to use another module in Topos, this ADS module, this kind of grid-like symbol up here. So you click that and click Options. And again, it seems like there's quite a lot of options here, but as long as you follow this guide and just stick to only ticking a few boxes, then it will work in most cases. So what we're doing here is we're creating a simplified net. We're not calculating a tiling, we're just simplifying a crystal net down to the central atoms that define the molecules. And if you want to keep like local bonding information, then you want to do this keep initial structure here. So this is what you need for the new crystal grower. So this will save the locations that these interactions are coming from, so for bidentate and stuff like that. Then we'll go to the topology window, and again, most of this you don't need to mess with. The only bit that's important here is the bond types. So this is how you define the connectivity between molecules. So if you want to keep valence bonds only between your atoms, that's what this window means here. So all of the bonds, all the valence bonds between atoms are considered. Hydrogen bonds between molecules are considered, and specific bonds we don't have, so we're just ignoring them. And van der Waals interactions are considered between molecules as well. So this is what you want for a molecular crystal or a molecular ionic crystal. These are the sort of bond setups you want. So if we click Run here, it's going to ask whether it can create a child database, which it always does when you're simplifying a net, but the first time you've done it, it creates the database. Asks you for your user code the first time like you did last time. And then it comes to this window here. So this is another important step. So for a molecular crystal, which are made of entire molecules, you can define the whole molecule as the central atoms of your net. If you're looking at say like atomic ionic crystals, then you'd have to select the ions as your central atoms of your net. But for urea, we can just click whole molecule. And you can see it generates it quite quickly. So we've got our new database entry. This is urea with a simplified net overlaid on top of it. So if we visualize it with CrystoGen, you can see it's created these dummy ZA atoms at the centers of each of the urea molecules. So that's your simplified net, but you can see it's also retained the original urea molecules underneath. Now that we've generated our simplified net, we can look at the structure file that's been calculated. So you can either do that by selecting the database entry, pressing F9, or you can right click and press View. So if you press View, you can see your generated structure file. You've got your 14 neighbors. You can see you've got one molecule of urea and then a second molecule of urea in a different symmetry position. And you can see this line here corresponds to all of the neighbors to this molecule in the unit cell. So there'll be 14 entries here corresponding to the 14 neighbors here. There's a detailed discussion of the format of the structure file in the CrystoGen manual. So we can't just save this file here like we can with zeolite. We actually need to generate a companion file to this, which corresponds to these neighbors here. And it contains the information of the energies that we want to assign to these interactions and the interaction types that we want to recognize. So something like hydrogen bonds versus van der Waals interactions would be different interaction types. And these types are decided by the point group symmetry of the molecule. So to generate this, we can click Database, Export, and we can choose a folder to export to. So I'll just select where the database is saved and call this Urea 14. And if we navigate to that folder on our system, you can see it's generated these two new files. So we'll view these in text editor and line them up side by side. So you can see on the left hand side we've got this bonds file, which is our net interaction energy file, and on the right we've got our structure file that we were just looking at. So with 14 neighbors, we've got 14 interactions here. So you can see you've got 14 lines here, which correspond to 14 interaction types. But these are now divided into different interaction types. So if some interactions are the same based on symmetry, the point group symmetry of your molecule, they'll be assigned the same number. So you can see we've got 2 interactions of type 1, 2 interactions of type 2, 1 of type 3, 1 of type 4, 2 of type 5, 2 of type 6, and 4 of type 7. So those 4 are actually the ones that are removed when we increase the strength cutoff using omega. So we've got 14 interactions, but 7 interaction types. And just looking at this line a bit further, you can see the origin species. So that's what type of species it is, and so that's what the A stands for. It also corresponds to that dummy atom that we saw in the visualization stage. And this 1 here corresponds to like a symmetry position or a type of that molecule. So if you saw 2A here, it would be the same composition chemically, but it would be a different coordination or symmetry position. Then we've got the origin species for the interaction and the destination species for the interaction. This is only important when you've got more complicated systems where you've got say you were using a solvent or something and you didn't want to just represent it by its chemical composition. If you wanted to know exactly which species it was connecting to, that's what these ones correspond to here. And then you've got the translation, so this is like related to the symmetry operation you'd have to perform on the destination species. Then you've also got the bond length in angstroms here. So there's a correspondence between these files here. So this interaction number 1 here corresponds to interaction number 1 here. So your neighbor here, which triggers this interaction, is species type 2, and it's in the unit cell translated 1 in the x direction. So it's +1 in the x direction. And then there'll be an interaction for each of these neighbors here. So now that we've looked at the interaction types, we need to look at the interaction strengths. So that's what these bits down here are. So we had 7 interaction types, so we've got 7 interaction strengths here. What these values correspond to are the Voronoi face size calculated in ToposPro. So when we calculate these Voronoi polyhedra, the size of the face correlates to the interaction strength. So it's kind of related to how close the species are to each other. So if something's closer, then it'll probably have a larger Voronoi face, and it will have a larger interaction strength estimated. These are the first approximation generated by ToposPro, but they don't really correlate with the free energy of crystallization because there's no consideration of desolvation. So even though topologically they should be stronger bonds, there may be a higher penalty for desolvation in certain solvents versus the energy regained when adding to the crystal. So it doesn't necessarily mean that a stronger bond would mean a stronger free energy of crystallization, because it cuts both ways. It may be a stronger interaction with the crystal, but it's also going to have a stronger interaction with the solvent. So these are likely going to require adjustment. So what's going to happen when you're running simulations in Crystal Grower is you're going to be changing these values. So you're going to look at these interactions and make some educated guesses based off of solvent coordination. Is it a hydrogen bonding solvent? Is it a polar solvent? And that can help you make some judgments on what energies should be largest. In the user interface of Crystal Grower, you can change these directly within the program. But if you're using the command line interface Crystal Grower, then you'll have to go in and manually edit these in your files. And if you scroll down to the second molecule, you'll see that they're in the same order because they're defined by the point group of the molecule. So as long as your molecule's in the same coordination, then these interactions are exactly the same following down here. So if you change one of these, you should change this one, the corresponding one down here as well. That's automatically done in the user interface, but again, something to consider when you're using the command line interface version of Crystal Grower. So that's just a quick guide of how to create a structure file from a CIF file and its corresponding bonds file. This is for molecular crystals, like we said before. Zeolites are a little bit easier and covered in a separate video. But this is just a quick guide showing you how to get a first approximation of a structure and bonds file using ToposPro. There are more advanced techniques for generating the adjacency matrix at the beginning, but I'll cover that in a separate video.